In this video, I will show you how to find the absolute maximum value of a function when you are unable to use a candidates test. This problem is considered calculator active, so we will use our graphing calculator as needed. It is given that the velocity function v of t equals 1 minus arctangent e to the t power. So go ahead and hit your y equals button and type this velocity function in as y1 or y2. Part C. Find the time t greater than or equal to 0 at which the particle reaches its highest point. Justify your answer. When we talk about the highest point, we are talking about the absolute maximum of the position. When we look for the absolute max, normally we use a candidates test. However, we can't do a candidates test this time because we don't have a closed interval. In order to do a candidates test, we need endpoints like 0 and 5, which we don't have. We can find the absolute max without a candidates test as long as the position function turns out to only have one critical point. If a function only has one critical point, then a relative max will also be the absolute max. This makes sense because if we have a relative max like this, and let's say we don't exactly know what happens outside of this small window. However, if this is the only critical point, then there's no way that the function will bend back around and end up higher than this point. Because if the function did bend back around, guess what? We would have another critical point. If there are no other critical points, there are no other bends in the graph. So a relative max will definitely be the absolute max as well. To find the critical points of the position function, we need to find where the derivative equals 0. In other words, we need to find where the velocity function is equal to 0. We have the velocity function typed in as y2. Let's take a look at the graph and see if we can find where the velocity is equal to 0. So this velocity graph does seem to have only one critical value. Let's find what that is. So hit second trace, and we can use the 0 feature, so option 2. When it says left bound, slide over a little bit to the left of where the intercept is and hit enter. And then it says right bound, slide to the right of the intersection point and hit enter. And then when it says guess, just go back close to the intersection point and hit enter. So there it is, 0.443. So we just saw that t equals 0.443 is the only critical value of the position function. If this turns out to be the location of a relative max, it will also be the location of the absolute max. So how can we tell if this critical point is the location of a relative max, a relative min, or neither? Our favorite tool for identifying the location of a relative max or a relative min is the first derivative test. So let's make a sign chart of velocity and see what happens at the critical value. From the graph, we can see that velocity was positive on the left and negative on the right as it goes from above the x-axis to below the x-axis. According to the first derivative test, the position function has a relative max at t equals 0.443 because the velocity changes from positive to negative. Since t equals 0.443 is the only critical value, this relative max is also the absolute max. Let me emphasize one more time that usually when they ask us to find the absolute max or the absolute min, we use a candidates test. But that only works when they give you an interval with endpoints. If they don't give you an interval with endpoints, check to see if there is only one critical value. If so, any relative max will automatically be the absolute max, and any relative min is also the absolute min.